Welcome back. Well, of course, our energy development wasn't going to end quite there. Let us now talk about a particle of mass m whose total energy is twice its rest energy and that collides with an identical particle at rest. If they stick together, what is the mass of the resultant composite particle? What is its velocity? Okay, we got a lot to deal with here. Let's be very careful on how we define everything. Our relativistic energy equation actually is a square because of the invariancy, which is E squared minus P squared C squared is equal to M squared C to the fourth. This is the actual equation that Einstein had, although the rest mass of E equal MC squared is most commonly known. So let's be aware that those two come together because we have an energy momentum 4 vector, and that's why we have to have the invariance like this. That being said, let's see how we deal with it. Alright, so of course we have a conservation style question going on. So we need to know before and after. So the initial momentum we have is EI squared minus PI squared C squared, and then we have M squared C to the fourth. But we were told that the energy was twice that of the rest mass, hence 2mc squared. So if we square everything, then we're good to go. Now we just got to solve for the initial momentum pi, so p initial, by minusing everything over. So add that over, minus the m squared t to the fourth, and let algebra do its thing. We see that once we do that, we can kind of taper off, take the square root of both sides, cancel a c out, so we're left with some factor of mc. So pi is equal to root 3 mc. Okay, so far so good. The initial energy, though, was equal to EI is equal to E1 plus E2, which was twice the rest mass plus a rest mass. Okay, because that was the total energy of the configuration before. And that gives us three rest mass energy, and that's where we get the 3mc squared there. Each is conserved, so EI is equal to EF and PI is equal to PF. So after the collision, of course, we got to do the same thing. Except on the right-hand side of the momentum equation, we have a big M since they combine. And if we solve this, and we see that they're conserved, now we can start playing the game. Notice that EI has to equal EF, and PI has to equal PF, so we can plug into PI and EI with the substitution accordingly. So what we do here is that this is the EI that we substitute in. This is the PI that we substitute in, of course, times a C squared term there. So once we square everything, of course, we get 9 m squared c to the fourth minus the square root of 3 squared gives us 3 m squared, and then we have a c squared times a c squared, so c to the fourth. So everything works out unit-wise. They combine down. We see that the c's cancel. And we see that big M is a combined mass of square root of 6m. Thank you, conservation, for making this happen. But however, we also know in the same perspective that since P is equal to gamma mv and E is equal to gamma mc squared, we can substitute the momentum by solving for gamma m as highlighted in red. So momentum over V is equal to gamma m. And we can sub that into the energy equation, and that's where we get P over V C squared. So if we're looking for V, we can get the PC squared over E term, and we see that we know what's going to happen based on the conservation. So we get C squared cancel, we get M and M cancel. We see that 3 is just the square root of 3 squared, so we cancel a factor of that. And we see that V is equal to 1 over the root 3 of C. And if we just wanted to keep things rationalized, we would have just had root 3 over 3 instead of canceling the square root. That's a choice of reference. If you're a mathematician, you want to rationalize. Here, it doesn't really matter. You might be even better off with the decimal point. Point is, we know that the velocity has to be some fraction of the speed of light, so we're good to go. Mass, of course, joins together, and they join by a factor of square root of 6. So this was a real fun problem to help us get used to momentum and energy. But note that if you want to find the momentum, you have to use this big equation. and be very careful with it. And then energy, you just have to be careful what's moving, what's not, and modify accordingly. So that being said, we definitely have more work to do with this soon, and we will see you there.